Okay, welcome back. So last 3 lectures. Next week I'll probably discuss some Bayesian testing stuff, and just to give you kind of an idea of what Bayesians do. I'll write it down generally, but there's a lot of issues and you have to ask questions about which priors and when and that same discussion. So a more thorough discussion would appear in Bayes class. But I'll try to fill in some of that stuff, and I won't test you heavily on that in the final. So things are about to ease up a little bit. I do want you to understand the Neyman Pearson lemma. There'll be a couple warning shots that I'll give you on Monday about this, about what it does not say, that people get confused about. Midterm back on Monday. I'm still in the midst of those. I don't want to rush it. I will offer you the same thing, that if you want to go back through the midterm and correct everything, you can turn that back in for the half credit. You can turn in everything at the final exam. So I'll give you also a little bit more of a reprieve. Our final exam is scheduled for Saturday morning. Is that right? So that's a little bit rough. What I would like to do is give you a take home and alleviate some of that pressure. Just because I don't like that it comes so soon. I also want to give you enough questions that kind of recap everything in the course. So this will make it a little bit easier in terms of what do you have to study and how much do you need to know. I want you to know all the content in the course. I know that's a little bit impossible, so I'll just give you a few extra questions than I would give you during an in-class final exam, and hopefully it'll help recap everything, and you can use all your resources as well. If you're practicing for a qualifying exam or something like that, you might want to see how far you can get on an exam like that and actually time yourself, and then go back and clean it up later. So that's what I would recommend to you. I know that's a little bit difficult to do when you're not forced to do it. It would be hard for me too, but I would still try and attempt to do it. Sit down for 2 hours. How far can I get without opening it? I will give you until Wednesday at 5 p.m. to turn this in as well. And so I'd like you to write it up neatly. It doesn't need to be LaTeX or anything like that. I'd probably advise you don't worry about LaTexing something this late in the game because it'll take you extra time. I know that that's limited right now. But write it up clearly, and then you'll email it to me. And so we just send it to Lemman@vt.edu. And in that same email, you can include your homeworks. You can include your extra credits if you're still looking to turn those in. You can include your midterm makeup as well. So you can include all of that stuff. But I need to impose a strict cutoff of Wednesday at 5 p.m. because I need to spend all Thursday going through everything. So it'll take me all day to do all of that, and I need to have my grades in on Friday. So
Wednesday, like Wednesday after Saturday?
Yes, not the one before.
You just like Wednesday. It was very vague.
Okay, fair enough. So it'll be due on the following Wednesday at 5 p.m. So this will be, I'll email it to you. See, email it out. It'll be probably Saturday morning. When I say that, probably at like 1 a.m. or something like that, I'll send it out to you so that you can wake up to it. So get started on it.
This coming Saturday?
Not tomorrow.
Tomorrow?
Yes.
Cool.
Not tomorrow. We have 2 more days of lecture. And we'll try to recap and summarize at least a lot about this testing. Again, I can't fill in all details, but I'll let you know where the debates occur. So emailed out Saturday morning. That's in 8 days.
May 7th.
May 7th. Yeah, exactly. May 7th. And then it'll be due on Wednesday. This is the following 11th. At 5 p.m. And everything will be due at that time. I'll remind you of all that. I'll send you an email. And I'll say all of this. So just wait until that Saturday. But that's what's coming. So hopefully that lightens up a little bit of the pressure for you. And then we'll do a review on Tuesday, this coming Tuesday. So just to recap anything, if you have any questions about stuff, we can try to handle it there. So that'll be business as usual. Any questions? Okay. Let's go through another example about power and power calculations. This is in the book, and it'll kind of tell you about the trade-off in type 1 and type 2 errors. And I'll address that trade-off when we go through the Neyman Pearson lemma. So we did write this down at the end of last time, so I'm just going to tell you what this is, and then we'll circle back around to it. So Neyman Pearson says if 1 is true, and it has a criteria. So this is a rejection region. And the rejection region is defined by this criteria right here. So this involves both the null and the alternative. So I'll just remind us that this is for the simple versus simple case. This is H naught, theta is equal to theta naught, versus H1, H alternative. I don't know if I call that H1 or H alternative, but I kind of flip-flopped in between those things. They mean the exact same thing. So I think I say H alpha. That's theta is equal to theta 1. So this is the simple versus simple test, and this is not a controversial thing. And this can all be extended to the one-sided test if I consider points in theta naught to the left of some boundary and theta 1 to the right of some boundary. Everything will extend from this. And so that's just a corollary, is the one-sided test. The two-sided test does not extend from this. So you have to put down another condition to unbias the test. So I want to just point out, for the one-sided power function that we worked out last time, it was monotone. And that was very nice. And so when you have monotone power functions, monotone likelihood ratio tests, essentially, then all this stuff kind of makes sense. If you have to impose another condition, bring in another constraint, it's because the problem isn't solved. And it turns out there is no UMP test for the sharp test unless you put it into another subclass. And so people forget that. And so the sharp test does not enjoy or share the same properties as the one-sided test or the simple versus simple. So I will say this, it's still uniformly most powerful with a caveat that you're in this confined subclass and the likelihood ratio test is not monotone. And that's what everybody starts arguing about. And so understanding that is the key to understanding the argument. I'll say more about that on Monday. So we'll come back and we'll prove this, that if a test satisfies this, that the rejection region is defined by that, and it's a size alpha test so that the max type 1 error is alpha, right here. Then the test is UMP and it's size alpha. The size alpha comes for free because of this. So, but this is basically saying if it satisfies this condition, it's UMP, uniformly most powerful. What that means is that the power in the alternative space is higher. That means that the type 2 error is lower. So the power, 1 minus the power in the type in the alternative space is the type 2 error. So this right here is the likelihood ratio test in disguise. And we'll look at that as well. So what it's saying, what Neyman and Pearson are saying is that if you follow the likelihood ratio test in the simple versus simple or the one-sided case, and you calibrate the test to be size alpha, it will be uniformly most powerful, so it'll have less type 2 error than any other test out there. And so there's some reason to think that that's a good idea. So that sharp testing situation, this does not apply directly to it. I think people forget that. So the sharp test is where all the controversy lies, for kind of fairly obvious reasons. But here's more technical reasons. We'll prove this in a moment. I want to show you just one more example on power to show you that there's a trade-off. So I said size alpha throughout all of this. I will address the comments that they make about level alpha tests. So just remember that the max, when theta is in the null space of the power function, this thing is equal to alpha. That's a size alpha test. There's a small caveat they address when they end up saying if it's less than or equal to alpha, they say it's a level alpha test. And they make a lot of claims in this proof about level alpha test. We can forget about all of it. So if they end up doing it in one part of the proof in the book, where they kind of say, thus, it's size alpha, it's level alpha, so it's size alpha. So it's like, if they're the same, then why are we differentiating? And so it's obviously the same in this case because the hypothesis is simple. And that's why they can do that. It's only one point that you're addressing. The whole point of talking about the level alpha thing is saying that if you did end up decreasing the type 1 error, so making it level alpha, so if you are just making it smaller and smaller, I'm going to have a trade-off, and I'm going to increase the type 2 error. So that if a test is level alpha compared to a size alpha test, so if it had less type 1 error, it's going to incur more type 2 error, so it's going to be less powerful. So it's just putting a bound on the statement, that you can't wiggle this thing around and make it smaller and get higher power. You're going to get less power if you make that smaller. So that's the trade-off. Let's see that trade-off explicitly, and I'll try to sweep that under the rug when we prove this. Because it really is, you can substitute size alpha for everything, and then at the end you can say this also applies to level alpha because decreasing the type 1 error even more is only going to increase the type 2 error of the other test that we're going to compare to. Hopefully that'll make sense in a moment. So let's look at this example right here. So X is binomial, there's 5 20 flips. This is the probability of success. So typical setup. I'm going to consider 2 tests. So test 1 is going to reject. Oh, and I should probably tell you what the hypothesis is. So here's the hypothesis. So this, again, would be a fairly uncontroversial test in my book, if you wanted to test these 2 things. So H naught is theta is less than 1/2, and the alternative is theta is greater than 1/2. So I'd say those 2 sets are fairly comparable to each other. Test 1, we're going to reject if X is equal to 5. And that kind of makes sense. This is an extreme condition on testing this, that if X was 5, so if I ended up saying my hypothesized value was maybe theta was equal to 0.1 and I saw 5 successes, I wouldn't believe you. So I think that it's extremely unlikely. So kind of makes sense. If I ended up saying I'm going to reject if X was equal to 1, would that make any sense for testing this hypothesis? No. Because it would end up putting more power in the null space than you should. So you wouldn't want a high probability of rejecting in the null space. So that would bias the test. So I think it makes sense that the only values you would want to test to reject this null hypothesis is that if we had over half of the observations being successes. So that would be a 3, 4, or 5. So the values could be a 0, 1, 2, 3, 4, or 5. There's 6 values in there. So 3 of them, by symmetry of this problem, kind of makes sense to at least think about if you're going to reject this null hypothesis. So this would be very extreme right here. In test 2, we're going to look at this test as well and look at its power function. We're going to reject if X is equal to a 3, 4, or a 5. I just want to point out, it wouldn't make sense if we plugged in a 2 in here, because under the null hypothesis, that wouldn't be a very unlikely scenario if I saw 2 successes. If I saw 0, 1, or 2 successes, at least conceptually, it would support that null hypothesis. If I started including that in the rejection region, I would bias the test. We'll come back around to that on Monday and look at what bias tests are. So most tests kind of make sense. This is just a more extreme test right here. So this is the rejection region. We didn't drive it. We just stated what it was. So likelihood ratio tests give you a way of deriving tests and calibrating them. So we've just picked these two tests to compare. So the power function for test 1 is just the probability that x is equal to 5, given whatever our probability is. And I've been writing it like that all semester, so I'm going to continue with that notation. So this is given whatever the parameter is. So what's the probability x is equal to 5? What's that?
5cx p raised to x 1 minus p raised to x. But p is there.
Yeah. I think I got it.
Yeah.
So theta to the 5.
Okay.
So probability of success 5 times. So theta times theta times theta times theta times theta. Theta to the 5. So the power for test 2. Would be the probability that x is equal to a 3, 4, or a 5. So this would be our rejection region. Given whatever theta is, what's that? That's 5 choose 3 to the theta to the 3, 1 minus theta to the 2, plus 5 choose 4. I could write that out as a 1. I'll just tell you where all this stuff is coming from. And I guess I'll write it out. 5 choose 5, theta to the 5, 1 minus theta to the 5 minus 5. That's what parallel was saying. So, and this thing is theta to the 5. So that was that. Right there. So just this binomial formula. That's the cumulative probability over everything. So those are our 2 different power functions. Let's draw these. So I'll draw you the power function for test 1 first. So this will be theta to the 5, looks something like this. Some increasing function. So this is going to be theta 1, theta. And I'll call this beta 1, theta is equal to that. And this will be beta 2, theta. Our power function for our second test. So it looks something like this. Half is over here. The null region is over here. The alternative region is over to the other side. So I could end up looking at what that probability is right there. So this is the max probability of the null set right here. It's obtainable. And so the size of the test is right here. So this would be alpha in this case. So that's going to be 1/2 to the 5. Does anybody know what that number is off the top of their head? Can you, what is it?
130.
Yeah, it's a decimal. So I still don't know what that number is. Sorry. I didn't pass the 3rd grade. So, does anybody know approximately what that is? What is it?
031.
0.31. Yeah, I kind of like that. That's pretty close. 0.03 in the ballpark. Very good. Piper could do this. I think it is 0.31.
031.
Yeah. 0.31. Check you out. Not bad. So, good estimator. Too bad you don't get credit in my class. So, 0.031, something like that. So it's relatively small. And I could ask the flip question is what's the probability of making a type 2 error? And so obviously the type 1 error is small, but the type 2 error is pretty extreme. And that's because this is a very extreme test. So it's guarding against a type 1 error, but it's willing to make error on the other side of everything. And so here's the question. What if we wanted the type 2 error to be bounded by a half? So they present this in the book. And obviously we have two recourses. So you could try to bring that down by cranking up the number of trials that we end up seeing. So n was 5, I could crank that up and try to bring this down. But if you only had 5 data points, then there's only a certain number of values right in here where we would have a type 2 error that's less than a half. So if I wanted to look at the type 2 error, look at when it's less than a half, it's for these values over here. So the power is going up, the type 2 error is going down. And so to get that value right here, we would need to look at 1/2, and I just need to invert the function, so to the 1/5. So what I would need is I would need values of theta that are greater or equal to 1/2 to the 1/5. Piper.
No.
You can't do 5th roots in your head.
That's where I draw the limit.
Yeah, I draw them at 3rd roots. So you're way ahead of me. So it's like 0.87. Something like that. About 0.87. So for values that are greater than that, right there you can have this type 2 error, less than a half. So there's this big trade-off right there. You might want to think about this in terms of calibrating delta, how far out you would need to be before you could detect a meaningful difference. And so, and a lot of people think about that if they're thinking about the power curve. So I think you should not do any sort of Neyman-Pearsonian testing whatsoever, or do this sort of thing until you're willing to talk about that meaningful difference and seeing how far out you would need to be to reduce some other type of error. If you're only thinking about p-ducking alpha, you haven't thought about the power curve, and you're just looking at the type 1 error, and that's it. And so, you know, I'll leave it at that. So this is a little bit different right here. You could draw this. And so this other curve right here is a little bit bigger right here, but there's kind of a trade-off that's made. And so the type 1 error is a little bit bigger right here, but the type 2 error is coming down over here. And so this would be our power curve for our upper test. You can draw that out. But basically, any trade-off that you make in the null space, you're going to feel in the alternative space. So if you try to reduce the type 1 error, you'll increase the type 2 error. And I think that makes sense. So that's all this says. You can go through that whole thing. We won't try to invert this and come up with meaningful values because I don't think Piper's up to the task at this point. So anyway, that's what that is. So there's this trade-off. And I think the only place that's important in the Neyman-Pearson lemma is to see this trade-off, that if I reduce the type 1 error even further and I discuss the level alpha test, I'm only going to increase the type 2 error. So that's the trade-off. We'll stick with the notion of size alpha test throughout the proof. Let's do it. So there's a few layers to this proof. And I would like to propose nobody should be doing Neyman-Pearson testing until they understand this proof. So basically what I'm saying is nobody should be doing this. So you have to be careful with all of this stuff. Again, it's the sharp test that is the major culprit. So I don't think that there's any great controversy in one-sided testing. So there are some key values that I'll accept as something reasonable. Sharp test, I don't like it. We'll go into more about that on Monday. Let's just prove this statement. So here's just a little bit of notation. So let delta x be equal to a 1 or a 0, and this is going to happen if we're going to have this condition that I've written down over here. F of x given beta 1 is going to be greater than k f of x given beta 0. This is going to happen otherwise. Beta 1 less than k times f of x given beta 0. So this is our test. It's just an indicator on whether or not we've rejected. So this is some test, and it follows this. It follows condition 1. And so we're also going to let this test delta x have size alpha. So I just have some test that follows this condition, and I'm going to calibrate it so that it's of size alpha. I want to just point out that this test is the likelihood ratio test. So just note, our rejection region is defined by f of x1, f of x given theta 1 is going to be greater than k f of x given theta 0. Just want to remind us, k is something that's strictly positive. So I'm just going to do a little bit of adjustment of this equation. This is going to be 1 over k is going to be f of x given theta 0 over f of x given theta 1. It's the same exact thing. I can get rid of the equal sign if you'd like. Keep it exactly the same. So what does this say right here? What's the range on this? This is 0 to infinity. So what I want to point out is the likelihood ratio test. The way that we studied it at the very beginning is we looked at this thing right here. This is going to be the maximum over theta is an element of the null space, likelihood, over the maximum of theta in the alternative, well, it's the unrestricted maximum. So I'll say that's an element of the null or the alternative. I'll put a union right there. Likelihood function. And since this was baselined in both the null and the alternative, this thing, we said we're going to bound it by some constant c. In this constant, it's going to live between 0 and 1. I guess we have inclusive 0 and 1. And so what I said before is if I get rid of the null space in here, it changes the constant and it makes it go between 0 and infinity. And I probably should get rid of the inclusivity. That's not going to happen. So that's the only thing we've changed right here. And so we adjusted the likelihood ratio to this right here where we've just changed the range. Think about what this is. This is the maximum over the null set because it's only 1 point. This is the maximum over the alternative set, And so I've just rewritten the likelihood ratio a little bit different. This is just the sampling distribution right here, but I'm thinking about it as a function over theta when I plug in the thetas, and so that's a likelihood. So how do I get likelihoods? I take our sampling distribution, I think about them as functions of the parameters. So this is the LRT. They never say it. So they make that connection. It seems to be confusing. Okay. So Neyman Pearson addresses the likelihood ratio test. Get rid of all that. Okay, so that's our test. So this is basically just an indicator of rejection. So delta x is 1, we've rejected. Otherwise, we haven't rejected. Whatever you want to call that thing. Okay, so let delta x prime be some other test. And they say in the book, let it be level alpha. So meaning that if we reduce the type 1 error even further, we're only going to increase the power. We're going to decrease the type 2 error. Or sorry, we're going to increase the type 2 error and decrease the power. And so this other test will still be more powerful. So I'm going to say that it's size alpha. Just to make everything simple. It is, if it's level alpha, it's size alpha in this case, because it is just 1 point. So don't get too hung up on that. Okay, so we're going to show that this test right here is more powerful than that test. So here's the proof. Here's the master equation for this. This is the thing you need to remember. Everything comes from this equation. So they tell you in the book this is true, and they move on. So the book states this thing right here is greater than 0. And so they do that thing most books do, where they say, obviously this is true. Next slide. So I do recall when I read through that, I was like, I don't see it. You know? So saying that, how do you check? You start plugging points in. And that's how you check to see if an equation is true. How do they think to do this? I'm not sure. So it makes sense now that I know the punchline of the proof. So obviously this is a well-constructed proof, and somebody's thought about this and laid all the foundations for it. All we have to do is remember how they constructed it and gain insights about that in the future. Let's just check this out. If this is a 1, we've rejected. So if that's a 1, so there's only like 4 possibilities here of what can happen. So that can be a 1, so we rejected. Let's look at our possibilities. If this is also a 1, right here, then this is a 0. And so that's true. If this test is a 1 and that's a 0, this is positive right here. If this is a 1, what's that? Is it positive or negative? We know. It's positive. So if this is a 1, this thing is a positive over here. This was positive before, but we didn't care because the leading term was a 0. Anything I multiply into is still 0. So if that's a 1, this is positive, that's true. So this whole thing is positive. 1 times something positive is positive. So voila, very good. So if this was a 0, then we've rejected. Let's consider the easy case. If that's a 0 and that's a 0, that's a 0. Right here, it doesn't matter what I multiply into. This is true. It's positive or 0. In this case, it's 0. So if this was a 0 and that was a 1, that's 0. So this thing is negative. 0 minus 1 is -1 times something negative is positive. So all you have to do is check all 4 conditions. So that's true. Verify. Check. Now we can use this equation. So if that's true, if I integrate over both sides, it's going to preserve the bound. So this is also true. Integral delta x minus delta x prime times f of x given theta 1 minus k, let me get my braces right, f of x given theta naught. I'll fill in the missing step. I'm integrating over all of x. So I'm integrating over my x bits. This is also positive, or 0. So the 0 condition will be important. We'll use that in the second part of the proof for part B. I'm just going to write this out, what these terms are. There's 4 terms in here. I'm just going to expand every single one of them. So this is going to be delta x times f of x given theta 1 minus delta prime x, our other test, f of x given theta 1 minus k. I'll put everything in boundaries here. So the minus sign is that minus sign right there, and the k is this k that I'm factoring out of everything. So this will be delta x, f of x given, let's make sure I get them all right. So theta 1 minus theta 0. Yes. Delta prime x, f of x, given theta 0. Minus minus. Let's make sure we've got this right. So that one looks pretty good. That one looks pretty good, I believe that. That one is minus right there. Good. And then the negative, you have to be a little careful. So I think this is all right. So I just want to point out this is breaking into 4 different integrals. So I can drag the integration sign over all of those. And we're going to have integrals that look like this. Delta x, f of x, given theta I, I'll just say. And yeah, that could have an asterisk on there. I'll just leave it like that. Some delta function times some density. We'll just do it specifically so I don't confuse you. That's one of them. So which one is that? Let's do this one. Which one is that? That's our first term. So this is one of our integrals. This is going to be integral 1 that we're going to look at. I'll call it integral star. So what is this thing? It's an expectation of an indicator function. Indicator given theta 1, we'll be specific about that. What's the expectation of an indicator? It's the probability of that event. So that's going to be equal to the probability of delta x being equal to 1, given theta 1. So what is that? So if you have a hard time thinking about what's the expectation, why is the expectation of an indicator a probability, think about a Bernoulli model. So Bernoulli model is ones and zeros. The expectation of the Bernoulli random variable is P, the probability. So something that you guys know. So what is that right here? This is the power function. So this is the probability of rejecting prob of a reject given theta 1 is my value for theta. So that's what that is right here. So this is B theta 1. So that's the power. And this is the power in the alternative space. At theta 1, which is the element of our alternative. So once you know that, we're almost done. So this thing right here is equal to B theta 1 minus B prime theta 1. So this is the power of our other test. This is the power of our test that satisfies 1 and 2. This is power of some other test. Minus K. This is going to be B theta 0 minus B prime theta 0. I'm going to rewrite this. B theta 1 minus B prime theta 1 minus K B theta 0 minus B prime theta 0. You got braces, right? Okay, so we've got this equation. We're going to stare at this for a little while. We also know that this is bounded by 0. So I'll play around with this one over here. We'll do a little bit of manipulation, but we'll remember where the equation came from. So they're both size alpha tests. So that's the important thing to remember. So this is alpha, that's equal to alpha. What the book does say at this line of the test is they say that size alpha, you can let that one be level alpha if you want. So this will be less than alpha if you would like. You're going to decrease the type 1 error. This term will be positive right here. So it doesn't matter in what I'm about to write down. What we'll get is that B theta 1 minus B prime theta 1 is going to be greater or equal to 0. So if that's 0, this is true because we have that. It's bounded by 0. If this was positive, this would still be true because we've got a negative sign right here. So I'm subtracting off something that's big. And so in either case, whether or not this was size alpha or level alpha, this is still true. So what does that say? That's the completion to our proof. It says B prime theta 1 is less than B theta 1. So this is most powerful. I considered another test that was size alpha, and this test has a B. So if I decrease the type 1 error rate in the other test, it wouldn't help to recover any more power. So you'd only give up power. So that's A. So we proved the first thing. So what we just said, that if we satisfy that condition and we used it, then we can show that our test is UMP. And that was the punchline right here. The size alpha thing is coming for free because we've established the test is size alpha. So there's nothing to prove there. It could also be level alpha. Again, decreasing the type 1 error is only going to decrease or increase the type 2 error. Okay, the other part. So part B. So what we're going to assume is there's another test out there that's UMP. So we already know from part A that the test corresponding to this is UMP. So we know UMP, it's also size alpha. We just showed that. So let delta prime x be another UMP test. We'll say it's size alpha. This is the part of the book where they do the quick change on it. And they say, oh, it's level alpha, but it's really size alpha. How do you know it's size alpha? Because it's just one point that you're testing. So if that part confuses you, it's just because of the one point nature of everything. So they do just switch back and forth. So what we're going to do, this is the typical mathematical proof strategy, is I assume there's another test out there, and then we're going to prove those two tests are exactly the same. So there's uniqueness in this test. That's almost true. So let's just look at this. So we're going to go back to our master equation right here. And we'll have our test is UMP. And so what I know is those two things are both the same. Both tests are UMP, so these have to be the same. Same power. They're both most powerful. So beta 1 power functions evaluated at beta 1 are exactly the same. They're both UMP. So that's where we've used that. So we're doing slightly the other thing right here in the other direction of the proof. We first established those were the same. In the first direction of the proof, we established this thing was positive. I said it's 0, but you could consider the positive case. It doesn't change anything. So now we've assumed those are the same because they're both UMP. Now what can we say about this thing right here? It's 0 because they're both size alpha. And so this is going to be alpha minus alpha, so that thing is 0. So this thing right here is 0. So the whole thing is 0. So then we come back to this part right here and we see what this thing is. It's 0. So what we just established by assuming there's another size alpha test out there that's UMP is that all the terms right here, that's 0, these are equal to each other, those are equal to each other, and so this integral is 0. So this is what we established through that. And this isn't positive, but rather is 0. So going all the way back to this, what that means, if this is going to be 0 for all values, it says something about this leading function. It tells us that this must be equal to that. So if this is always 0, it means that thing is 0. Not quite. So measure theorists would say, oh, that's only true on all measurable sets. So there's some little unmeasurable sets where these two things can differ, but they're so tiny that they don't have any mass when you add them up. So that means delta x is equal to delta prime x. And I'll just put in a caveat on all measurable sets. That just means anywhere that this has a positive contribution to the mass, that this has any mass, then those two things are equal to each other. So they can jump away from each other for a little blip, but you'll never measure it and you'll never see it. So in my book, it doesn't happen. And in fact, in reality, that never happens, but we can be mathematical and imagine things. So again, I assume there's no continuums in the universe. So these are just in our mind. Enough of that. It's not a philosophy class. So what that says is that all UMP tests satisfy that it comes from a likelihood ratio test. So it's an admirable goal. What's the trade-off? You have to fix alpha up front, in all of this. And it applies to things like one-sided tests. So there's a problem in the book that says extend this and imagine all of this if I consider theta 1 and theta 2 on opposing sides of some boundary. And everything will work out exactly the same. Let's come back next time. Let's talk about the sharp test and all the issues. Then I'll try to do some justice to how does a Bayesian handle this and what are the Bayesian's issues. Because they're not free of issues. So that's it for now, guys. Enjoy the weekend.